All right, so this is an example illustrating how to use two different methods to graph transformations with four parameters. So in this example, the parent function is the reciprocal function, and we're going to apply these four transformations right here. And so the first thing we want to do is take the standard equation and identify which of these parameters represent the a, the k, the d, and the c. And so if you remember back to our standard equation, we have the fact that the A represents the vertical stretch, compression, reflection, and then we've got the K value, which is always next to the X, which represents the horizontal stretch, compression, reflection, and then we've got the X minus D and plus C at the end. So in terms of what we see here, the translation 4 units up, that's the C value. The 1 unit left is the D value. Now remember that X minus D is in the equation. 1 unit left means -1. So D is -1. When we look at in the equation, that would look like X plus 1, of course, when the two negatives are there together. So we've got those two values, and then we've got the vertical stretch by a factor of 2. So A is equal to 2. And then also, the reflection, we should consider whether that's a vertical or a horizontal reflection. So a reflection in the x-axis means we're going to reflect it this way, so it is a vertical reflection. That means we account for that by putting the negative associated with the a value. Then last but not least, we have the horizontal compression by a factor of 1/3. So just going back, we recall that horizontal compression, if something is compressed horizontally, we saw that it read as it was a factor of 1/3. So what that means is the k value itself is that value from the denominator. Okay, so this right here is just k. The factor is 1/k, which means that the k value is actually 3. So we've got those four parameters. Now what we can do is graph this two different ways. We want to always start by plotting the parent function. Now, for many parent functions, you've got multiple key points. For this particular function, the reciprocal function, we actually only have 2 key points. Now, we could plot many others. However, the best ones to work with here for the reciprocal function are just the values for when x is equal to 1 or -1. And we could plug in others. For instance, when we plug in 1, we get 1/1, which is 1. We plug in -1, we get 1/-1, which is -1. Now we could put in other values of x. For instance, if we wanted to plug in -5, we could take 1/-5, which is -0.2. And you could put that point on the graph, but you're going to realize that as you start plotting and transforming these points, that one's going to be pretty difficult to work with in terms of giving you a sense of where the function sits. So it's not that helpful in terms of plotting it. So what we're going to do, instead of using that as a key point, we're going to stick with using just the two values for x equals -1 and x equals +1. And we're also going to include the asymptotes. So we're going to plot those 2 points on the graph. And we're also going to include, there we go. We're also going to include the asymptotes, which define the boundary for these 2 parts of the curve, the 2 parts of the function. So the asymptotes for this function, if you remember back to the parent function, this function is bounded. It does not cross the x-axis and it does not cross the y-axis. It can't equal 0 in either direction. So we can plot now our function by simply just going through those 2 key points and having the function approach each of the axes, both the vertical and the horizontal. So there is our parent function. It's always good to label that on the graph, 1/x. We've got the 2 key points, and those asymptotes are going to also help us define where this exists. So now we can take into account the order. The order that we do these is important. So we usually start with the a value. It's always reflections, compressions, stretches first. So vertical reflections, compressions, stretches are the first things we were introduced to when we work with parabolas, so why not start with that? So if we've got an a value, of -2. What that means is that it's as we said, looking up above, it's a vertical stretch by a factor of 2, and it's also a reflection in the x-axis. So as I said, you can do this two ways. If you think about it visually, we can take those key points, which were both right here, and we can adjust those accordingly. So if it's a vertical stretch by a factor of 2, it means that they become twice as far away from the x-axis. So if they were residing at y equals 1, now they reside at y equals 2. Likewise, if it was residing at y equals -1, now it's at y equals -2. So there's the vertical stretch by a factor of 2. Notice that they've each doubled their distance away from the y-axis, and now there's a reflection as well, which means that instead of residing below, they're now residing above, and vice versa. So now we can take the points in this, rather than being at -2, it is at +2. Notice that the x value doesn't change. The other one, rather than being at +2, is now at -2. So what that tells us, notice here we haven't translated it yet, so the asymptotes are the same. And what it means now is, because of the reflection, the two quadrants, the two corners of the graph, are different in which this function resides. So now we can draw a line, and remember that this has been vertically stretched by a factor of 2, so we're going to notice that it's going to look further away from the x-axis, both above and below. Now, what we can do as well is we can take those, and as I said, do them in a table. So we can take the key points 1, 1, and -1, -1. And what we can do is take each of the translations and transformations and represent what happens to these points by showing our work using a table. So in this case, we're not affecting the x values for the first step, but what we're doing is we're taking the y values and we're essentially multiplying them by the a value. So we take the a value of -2, and we multiply all the y coordinates by that. So what that ends up looking like is we have the x coordinates remain the same, but we took the y coordinates and we multiplied them all by -2. So instead of 1, this became -2, and instead of -1, this became +2, and you can see that on the graph. So over here, the point that used to be at -1 is at -1, 2. Point that used to be at 1, 1, we moved down to 1, -2. So there we go. That's the first transformation. And now we can continue the next step by considering, once again, any other reflections, compressions, stretches, but now horizontally. So we have the k value being 3. So what we'll do is we can now say, all right, well, what happens to both the points and to the graph? So let's go to the table first this time. The k value, that means that it is a horizontal compression by a factor of 1/3, which means that the y values aren't changing now, but the x values are all 1/3 of their original value. So what that means is that we are multiplying by 1/3, or you can think of that likewise as taking the x values and dividing them by k, dividing them by 3. So the y values from the previous step are going to remain the same. The x values here are now all divided by 3 or multiplied by 1/3. Right? It's the same process. So we always take x and divide it by k. I should probably put the k down here. There we go. And so the x values now are going to change. The y values will remain the same. The y value was -2 and +2. Now the x values, 1 divided by 3 is 0.33, repeating. -1 divided by 3 is -0.33, repeating. Okay, so on the graph, we can take these points that we had in blue, and remember, we're always working from that last graph, that last step on the graph that we plotted. And we can take those points, and now what's happening is we are horizontally compressing them by a factor of 3. So graphically, we could take the point and we could move it if it was sitting at -1. Now it's sitting at -1/3. If this was sitting at +1, now it's sitting at +1/3. And once again, the asymptotes don't change. So we can now graph this and sketch this by illustrating what that compression looks like associated to the key points. and it's still bounded by those asymptotes. So there in green, we've got y equals, and I should have included this equation for blue. Make sure you do label your graph. For blue, we had y equals, that was a equals -2, so -2 over x. And now for in green, we've got y equals not only the -2 over x, but now our x value has a 1/3 next to it in the denominator. So don't worry too much about simplifying that equation, but it does represent the fact that we have the a value and the k value. So last but not least, it's time for us to translate this thing. So from the table, we can see that each of the coordinates now are going to be moved. So something's being added or subtracted to them. So we're going to take the x over k value, and we see that the function has been translated 1 unit to the left. Okay, so d is equal to -1. So what we can do is we can take the fact that d is equal to -1, and we can subtract 1 from the x values. And because c is equal to +4, what we're going to be doing is moving it up 4, so we're going to add 4 to all of the y values. Okay, so the original y values from the previous row, or sorry, previous column in the table. So we're going to add 4 there. Means what we're going to get is, in this case, 0.33 minus 1 is -0.66. -2 plus 4 is +2. Likewise, the other point, -0.33 minus 1 is -1.33. And it's not essential to leave these as fractions because we're actually graphing these. So that's why these aren't exact values. And then 2 plus 4 is 6. Okay, so in the table we can leave those as decimals. The point is to be able to graph. So now we can take those 2 points and plot them. For this step, I actually think it's easiest if you take your previous curve, if you are using Notebook, and actually just move that curve. Now it'll also be helpful here to recognize that finally the asymptotes are moving. So if you wish, you can also use those as a guide. So you've got a couple of options here. The last thing that we just did was the green curve. So if I were to select those, here are the green ones, I'm just going to copy those and make them red. And along with them, actually, I should have also included the asymptotes. So I've got this one, and I've got this one. So what I can do is I can take those asymptotes, I'll also make those red. So notice that I can take those asymptotes, I can take them, or the curve, and I can essentially translate those. So we said that this was moving 1 to the left. So there we've got that moved 1 to the left, and then up 4. So there are my new asymptotes, and they will guide where these two curves reside. So now if I move these curves, I can see that these ones are guided by those asymptotes. So the 2 points on the red lines we have here down in the table are these 2 points right here. And if we moved our asymptotes appropriately and correctly, then those 2 points should sit exactly where we expect them to. So negative 0.66 and 2 is about right here. And you can see that that's sat on the red curve. And I can zoom in just a little bit and show you. Oops, that's not good. We're going in the opposite direction. Here we are. So you can see that that sits on right there. Okay, so you can see that point in red sits on the red curve. So it's negative 0.66 and 2. And then the other point in red from down below in our table, negative 1.33 and 6. So negative 1.33 is about right here, and 6 is kind of a little bit off of our graph right there. So we can see that that point is also going to be relatively in the same location where this point in green was. Remember, we essentially just moved the green curve upward. So you can see that that's where the key point is again. All right, so our final curve We have the transformations applied, the translations specifically, so we had -2 in the numerator, and then down below we had x over 3, or 1/3 x. And here we've got x plus 1, we said, because the translation was 1 to the left, and then at the end we've got the plus 4. So there's our final equation. Let's get the zooming down pat. There it is. And so the last step is to identify the domain and range. So that part should be easy, especially for a reciprocal function like this. You know, we've seen the asymptotes move, so now we can see or where the restrictions have moved as well. So the domain and range normally are all values except for 0. Now we can see that since this curve in red has been moved upward 4 units, and to the left 1 unit, that the domain is still all real numbers, except now the restriction is x can't equal -1. So it's a little easier to read this from the graph. Likewise with the range, y is all real numbers, y can't equal. In this case, we've moved it up 4, so y can't equal 4. And you can see that comes from the c and the d values. So previous examples with domain and range, we may have looked at the final form of the equation. So something like this, a little bit trickier to try to see where the domain and range, or what the restrictions are on it when you're looking at this format. But if you're looking at transformations and graphing them, that should give you a better sense of how to quickly identify the new domain and range of your transformed function.